Okay, I want to tell you a couple things about uniform circular motion that I think are a little bit confusing. So remember that when we're talking about uniform circular motion, and let's say that right now I'm going to make you a drawing where this is, let's say this is me standing on some ice, a very slippery surface, and I have a block of ice that I'm holding by a string. And it's very cold, so you can see my breath. So I'm going to take that block of ice, this one here, and spin it in a circle, all way around me. So if we were to watch me do this from the top, and this is not to scale, but if we were, let's say our eye was up here, and we're looking down from here, here's my eyelash, and we're looking at me do this, it might look a little bit like this, where I'm at the center, and there I'm spinning this block of ice. Okay, wait. If it starts over here, let's say the block of ice is here, and I'm going in a circle with a uniform velocity all the way around. Okay, you can see I didn't quite plan this very well, but I'm hanging on to that string, and the block of ice is moving in this with a velocity, in tangential velocity like this. And that velocity, as I move around the circle, remains tangent to the circle, which has special implications about the acceleration. And you recall that acceleration in general is equal to, it's a vector, and it's the change in velocity with time. Now, notice that when the velocity is constant in uniform circular motion, the velocity doesn't change in magnitude. So the length of this vector here is the same. What changes is the direction of the vector. And we had talked about that in class of how if at one moment in time it's, let's say V1 is there and V2 is over here, tangent over here, and we get, for example, the delta V is equal to V2 minus V1, or, and again, these are vectors, so it's V2 plus the negative version of V1. So this vector plus this one gives you the resulting vector, this vector here, the acceleration. So this is, anytime you have uniform circular motion, you will have this acceleration that is pointing towards the center. So everywhere on the circle, the acceleration is pointing towards that center, and that's called centripetal acceleration. It's pointing toward the very center. And it turns out that the value of that, AC, is equal to the velocity squared over the radius of the circle. And that's just a fact. So this is this strange fact. We have no friction here. All we have is the tension of this string now, and this acceleration, the centripetal acceleration, which we can compute, that is based on the radius of the circle and the velocity of the motion, the uniform motion. So the deal is, this is acting whether we are horizontal like this, or if we decided somehow we had the ability to spin the block up in the air like this. Now notice here we don't have to deal with gravity. Gravity still acts on this block of ice, but it doesn't really enter into the equation because the forces that we are concerned about are perpendicular to these forces, so they don't really affect the forces in this direction. we could compute the force of tension here. The force would just be equal to the mass times the centripetal acceleration. That's the force that you would get in that string. Now, if you decided instead to 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 spin this vertically, let's say up like this. Let me just kind of draw a little picture. I wonder if I can do that. Oh, let me see. I'll get rid of some of these guys. Oh, I can't. I will say now we're spinning. Now we're spinning like this. And let's say I had like some big, magic arm that I could spin vertically now. This block of ice. This is not to scale. Now the deal with this block of ice is that I'm spinning in this circle like this. Let's say the velocity is the same. I still have this centripetal acceleration. If the radius is the same, okay, you can see that these are, not to scale, but if this radius was the same and the velocity was the same, the centripetal acceleration was the same, even though now we have an extra force that has entered into it. Now we have gravity working here, and we have and by the way, gravity works everywhere. Oops, sorry, that's the wrong direction. Gravity doesn't usually go up. Gravity works up here, and by the way, it works over here too on the block. So gravity is pulling on the block at every moment that this block of ice is being swung around my magic arm, my really long magic arm. And so now when I compute the equation F net equals ma, I know the a is still the centripetal acceleration, but the F net is a little bit more complex because it not only does it involve the force of tension in the string, but it also involves the force of gravity that's pulling against it. Or at the top of the string, or at the top of the circle, the tension is going to be in the same direction as the gravity. So those are working together, but the acceleration is the same centripetal acceleration the whole time regardless. The only thing that changes is the net force. Okay, I hope this is helpful.